Bismillahirrahmanirrahim. Today we will discuss about a new biasing technique, another kind of biasing technique which is known as emitter bias. Okay, emitter bias. So this is one of the very stable biasing technique, and it is one of the very stable biasing technique. Stable biasing technique. Okay, and it is used in especially in application where good stability is required. For example, in military application. Okay, in military application. So military applications, etc. Okay, it is used in military applications, and this is one of the very stable biasing technique. That means the variation of IC and VCE with respect to the variation in beta is very less. So that's why it is very stable biasing technique. Now let us see the circuit diagram for this. You can see there is transistor. We will first do the transistor, and we will have RC, and this is VCC, and there is RE. Okay, and there is another power supply. So we need two power supply. Okay, and there is RB, and this is going to ground. Now you know that this should be forward bias, and this is 0.7, that is the base emitter junction is forward bias, and we need 0.7, and there is no voltage here, right? This 0 volt, or we can say this is ground. Now for having a forward bias, actually what we have to do, we have to connect this as, we have to use this VEE as a negative power supply, right? Negative power supply. Okay, it's DC power supply, and this one should be something a positive power supply. So this is the emitter bias. Okay, the circuit diagram for the emitter biasing. So we will be now performing some analysis to find the voltage VCE and the current IC. Okay, so we have the voltage VCE, because this is the collector, this is the emitter. The voltage between the collector and the emitter is known as VCE, and the current which is going into the collector is known as IC, and the current which is going into the base, we will call it as IB, isn't it? Now we will see how to analyze the circuit. Okay, for that we assume that we have RE, and we have got a VEE. Actually this VEE is actually it is negative power supply. Okay, and you know that we have something known as RC, and we have VCC. Okay, now this is RB, and this is ground, right? Now since this is negative power supply, you can have for example, you can give here plus 15, and you can give here minus 15, like this. Okay, now we will apply the Kirchhoff law. So the current will be going down, right? It is plus minus, right? Also this current, we can say this is IC. So that whenever the current enters under the resistance here, you can see that this is plus and this is minus. The voltage between the collector and the emitter, we will call, this is the collector, this is the emitter. The voltage between this is known as VCE, and this, since the current is entering here, is plus and this is minus. Now we can take a loop at the input side like this, and you know that the voltage at here, at this point, that is between the base and the emitter, the base and the emitter, and this is the collector. So base emitter voltage is 0.7. Since this is positive, you can see that the current IB will be going here, right, like this. Yeah, then this is plus and this minus, right? Now we will start writing the KVL in loop 1, right? Now you see this is plus, so plus IB RB, right? Then plus 0.7, and you have a plus IE RE. Then you can assume this also as positive, but actually you are giving the value negative anyway. While writing the KVL, you can assume that this is positive and the negative is grounded. You can assume like this, but while doing the problems, while substituting, you have to give the actual polarity of the voltage. Okay, so now I will write it is plus VEE, right? Since I am assuming it as plus, so plus VEE is equal to 0. Now you know that IE, so this is equation number 1, right? You know that IC is approximately equal to IE, right? Then, and also IC and also IB is, you know that IB is equal to IC over beta DC, right? So by using this, we can, by substituting these above notions in the equation number 1, we have, it is, the equation number 1 will be now rewritten as equation 1 become IB, we will substitute this IB with IC over beta DC into RB plus 0.7 plus, and IE we will approximate it as IC into RE plus VEE equal to 0. Now by using this equation, we can rewrite this equation as follows: IC into RP by beta DC plus RE is equal to minus VEE minus 0.7, right? So what is IC? IC is equal to minus VEE minus 0.7 divided by, you can write this first term like this, RE plus, okay, you can write like this. Then you can write this term RP over beta DC. So I am going to rewrite this equation. IC is equal to minus VEE minus 0.7 divided by RE plus RP over beta DC. So this is the equation for finding the IC. So we got IC now, right? And next we need to find VEE. So I will draw the circuit again. We have to find VCE. So I will draw the circuit again. You can see here, this is VCC, RC, and this is RE, RB, and this ground, and this is VEE. And the voltage between the collector and the emitter we will call VCE. The current is going down, right? It's the IC. You can also assume this is IE, but it is approximately equal to IC, right? Now we are going to write the Kirchhoff law in this loop, right? So we are assuming this is positive we are assuming this as positive, that means negative is grounded. This is only an assumption, okay? Actually, the power supply VCC is positive and power supply VEE is actually negative power supply. We need a dual power supply, dual mode power supply. Now we are starting from VCC. So since we are starting from the ground, right, we have to start from the ground. You have to start from ground and you have to go to, that means you have to end at the ground, right? So I am starting from the ground. At the ground it is minus VCC, then the current is going down, so this is plus and minus at RC. So plus IC RC, then you can see this is plus, so plus VCE, right? Then the current is going down, since current is going down, right, you see this is plus, so plus, instead of IE I will use IC, so IC into RE, right? Then again plus, so plus VEE, this is equal to 0. So what is VCE? VCE is equal to VCC minus VEE divided by, right? So sorry, it is nothing but VCC minus VEE, then minus IC into RC plus RE. So this is the formula for finding VCE. Okay, now we will draw the load line for this, load line for the emitter bias. Okay, so you know that first of all we have the x-axis and y-axis. The x-axis is VCE and the y-axis is IC, and we have the transistor characteristics like this. Okay, we have the transistor characteristics like this. This is the transistor characteristics, and this equation that you can see here, it is the equation of a straight line, right? It is the equation of a straight line. So we have already seen this, how to draw the straight line. You know, this is the x-axis and this is the y-axis, right? Now we will, to find the, now you know that the equation will be, okay, will be something like this. You can find the x-intercept and you can find the y-intercept. Now to find the x-intercept and y-intercept, to find the x-intercept, we have to put, find x-intercept, put y equal to 0. That means what? Y is IC. Put IC is equal to 0 in the above equation. So in this equation, if you put IC is equal to 0 in the above equation, we will get VCE is equal to VCC minus VEE. Am I correct? Yes. So this become VCC minus VEE. But you should remember that VCC is a positive supply and VEE is a negative supply. Okay, it's a negative supply. Now to find y-intercept, you have to put x is equal to 0, which implies if you put x is equal to 0, that means you have to put VCE equal to 0. That means IC is equal to VCC minus VEE over RC plus RE. So this is the method, right? So this is nothing but IC sat. IC sat is equal to VCC minus VEE over RC plus RE. So be careful, this VCC is a positive power supply in case of NPN transistor, and it is a VEE is a negative power supply. So when you apply this negative, this negative, negative, this kind of negative, this negative, the negative become positive, negative of negative become positive. That we will explain clearly while doing a problem. Okay, so next we will explain the stability of, that is the qualitative analysis of the stability of emitter bias. Okay, you know that in emitter bias we have IC is equal to approximately equal to IE. It is nothing but VEE, okay, minus VEE minus VBE divided by RE plus RB over beta DC, and VCE is equal to, you have already solved this, VCE is equal to VCC minus VEE, VCC minus VEE minus IC into RC plus RE, right? So these are all the two equations that you have seen before, and these are all very important equation. Now you know this is the circuit. I will redraw it. So this is VEE. Usually this is given as a negative power supply, and this VCC, and this is RC, and this is RE, and this is given as a positive power supply, right? So and this is RP, and we have a ground. Now what will happen when the temperature changes? We will see. And this is IB, you know. So when the temperature increases, you know that the beta DC also increases, or whenever the temperature changes, beta DC changes. Now it is very evident from the equation, this equation, that the term RB over beta DC is depending on temperature, right? But the effect of this beta is very less. Why? It is because as you, if you take the term 1, this is RB over beta DC, if the beta changes, you can see that actually it is containing a term of 1 over beta, right? As the beta changes, 1 over beta will be very small, right? It will be very small change. So because of this, you can say that the variation in the IC will be very less. Okay, or else you can explain the same phenomenon in the same way that we have described in the case of voltage divider bias. For that you can see the previous lecture. So you can see here, as the beta increases, beta DC increases, then you can see that the voltage VE also will increase. Because of this, if this voltage increases, the voltage at emitter increases, the current IB will try to reduce, which will results in reduction in IC, right? So whenever the beta increases, actually IC increases. So we can draw this phenomenon like this. So as the temperature increases, you can see that it will lead to the increase in beta DC. As beta DC increases, then it will increase the IC. Since the IC increases, you know that IERE, because VE is IE into RE plus VEE, right? Now the VE increases. Since VE increases, it will lead to the reduction in IB, and finally it will lead to the reduction in IC. So IC will decrease, right? So this will lead to the decrease in IC. Okay, so this is what happening in the case of emitter bias. Okay, now we will see a problem. So problem, so consider, determine, find the Q point of the circuit shown below. Okay, and draw the load line also find the load line. Consider, okay, sorry, assume that the transistor has beta DC equal to 100. Okay, so this is the question, and the part B, actually, if beta DC increases from 100 to 200, then what will be the percentage change in IC and VCE. Okay, the circuit is given here. Okay, this is the circuit. You have an RC, you have a RE, VCC, you have VCC and VEE, and the VCC is given as it is plus 15, and this is given as minus 15, and RE is 10 kilo ohm and RC is 4.7 kilo ohm, and RB is 47 kilo ohm, and this part is ground. Okay, now we can use the formulas that we have already derived. What is IC? IC is minus VEE minus VBE by, yes, we can use that formula. So the answer, so we are going to solve this. You can see that it is given given beta DC for the part A. Actually, it is given that beta DC is equal to 100, right? So we can calculate the IC. IC is equal to minus VEE minus VBE divided by RE plus RB over beta DC. Am I correct? I hope that is correct, right? RB over beta DC, right? Now this is equal to minus, you know that VEE is minus 15, so this is very important, you have to substitute minus 15, okay? Minus 0.7 divided by 10 kilo plus 47 kilo divided by 100, okay? So you will get IC as 1.37 milliampere, okay? Then you can find VCE. What is VCE? VCE is equal to, we will just write the formula. VCE is equal to VCC minus VEE. So this is the formula. So VCC minus VEE minus, yes, it is nothing but VCC minus VEE minus IC into RC plus RE. So this is equal to, what is VCC? It is plus 15 minus, and VEE, which is given as minus 15, okay, minus, and IC you have already find it, 1.37 milliampere, into RC is 4.7 kilo plus 10 kilo. So you will be getting the answer VCE as 9.83 volt. Okay, now we will see, so you have got now IC as 1.37 milliampere and VCE as 9.83 volt. So this is the answer for the first part. So the first part, actually it is giving you the IC and VCE, right? It is giving you VCE. Now what, so this is the case when beta DC is equal to 100. Now what will happen? So for the part B, so what will happen? What will happen if beta changes, beta DC changes to 200? So you can assume that this IC is IC1 and this is IC VCE1, right? Now we are going to find the changes. So when beta is equal to 100, you can see that IC, we will call it as IC2, will be equal to minus VEE minus 0.7 divided by RE plus RB over beta DC. So this is equal to minus of minus 15 minus 0.7 divided by 10 kilo ohm plus 47 kilo ohm divided by 200. So you can see this is 1.38 milliampere. You see here, if you compare with the old value, you can see that the change is very small, right? The change is very small. That's why we are calling it as a very good or a very stable biasing technique. Okay, now we will find what is VCE2. VCE2, you know that it is nothing but VCC minus VEE, okay, minus IC into RC plus RE. So it's nothing but, it is nothing but VCC is 15 minus 15 minus IC is 1.38 milliampere into RC is RC, you know, right? RC is how much? RC is 4.7 kilo, 4.7 kilo plus 10 kilo, I think so, right? It is 10 kilo ohms, right? This is 10 and this is 4.7. Now we got this is 4. Now you will be getting this value as 9.71 volt. So you can see here the change is very less. So if you are comparing this with the old one, the change is just approximately 0.1, right? Now we will calculate what is the percentage change in IC. So the percentage change in IC can be obtained by IC2 minus IC1. That is the new, this is the new, and this is the old one, right? That is for beta equal to 100. Old means beta equal to 100. You can say this is the old one, and these are all the new one divided by IC1. So you will be getting 1.38 milliampere minus 1.37 milliampere over 1.37 milliampere and multiplied by 100 to convert into percentage. That means it is 0.730 percentage. You see, it is less than 1 percentage. That is, the biasing circuit is highly stable. Okay, that's why it is used in military applications. Now we will see what is VCE, because in military application actually the soldiers will be operating the devices in extreme climate conditions, maybe extremely cold weather or extremely hot weather. So we need to prepare the devices or manufacture the devices to be suitable for any such kind of conditions. So now we will calculate what is delta VCE. Delta VCE is VCE2 minus VCE1 over VCE1, which is equal to, and you can here also actually forgot to multiply by 100. Now here you can multiply by 100 to convert into percentage. Okay, 100, which is equal to 9.71 minus 9.83 divided by 9.83, right, multiplied by 100, which is equal to minus 1.22 percentage. So this is also very small value. You can see this value is positive. It is because IC is increasing. Okay, and you can see this is negative. It denotes that VCE is reducing, right? So VCE is reducing. It is showing VCE is decreasing. Okay, and the percentage change in IC and VCE is very small, so we can say that this biasing circuit is highly stable. So it's one of the very good biasing technique. But one of the main issue is that you see here it requires a positive power supply, it requires a negative power supply. That means it needs a dual power, dual means actually two, dual power supply, which can give you positive as well as negative. So this is known as so we conclude with this. So this is about all about the emitter bias. Anyway, thank you for watching this. See you.